So we do know that kinetic energy means the energy it is possessed by any object by virtue of its motion. So this particular system where a mass kept at a particular position will have an energy possessed by that particular mass, and that particular energy possessed is known as gravitational potential energy. Whenever I keep any object at a particular position, innately that object will develop an energy within that particular system. Hey all, I'm Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence, and we were dealing with work, energy and power. And today we are going to see another type of energy which again you are all very familiar with. So potential energy. Potential energy is a term you have been hearing and seeing since you were in high school actually. So what exactly is potential energy? The general definition for potential energy is that it is the energy possessed due to, or it is the energy possessed by virtue of its position or configuration. That is, the energy possessed due to its position or configuration. So what does this actually mean? The energy possessed by an object due to its position or configuration. So we do know that only moving objects will possess kinetic energy. But what about resting objects? For example, this board or the smart board here is resting. Does it mean that it is not having any energy? See, when anything happens, there is obviously a release of energy or a conversion of energy. You do know that energy can neither be created nor be destroyed. It can only be transmitted from one form to another form. In curved spaces, that law is no longer valid, but still, as far as you're concerned, energy is completely conserved. So again, what about objects that is not in particular motion? For example, let's take a coconut tree. So if I'm saying that energy can neither be created nor be destroyed, then if I take a coconut tree and show you a coconut on top of that particular tree, does that mean that it has no energy? Okay, then suddenly the coconut fell. As it falls, the kinetic energy of that particular system increases, or the kinetic energy of the coconut increases and will have a maximum value just before it hits the ground. So where is this energy coming from? You know that energy can neither be created nor be destroyed. Then where is this coconut gradually gaining energy? Is it pulling surrounding air molecules and saying, okay, each molecule give me your energy? No, right? It is not doing that. So where does this coconut, while falling, gradually gains kinetic energy if it cannot create energy out of nothing? So the next fact also is that when we drop objects, it actually breaks. If this was a watermelon that was falling from a severe height, you would have observed it impacting the floor and instantly be crushed. Right? So why does this happen? Why does an object suddenly gains kinetic energy as it is falling from rest, and suddenly when it hits the ground, it breaks? Sometimes it breaks, sometimes it just jumps off and or rolls off or something. But the part we are going to concentrate is, why does the kinetic energy suddenly increase, and is any energy possessed by the objects that is in rest? So obviously you will know that it is potential energy because it is the energy possessed by an object due to its position. For example, any object when it is kept at a particular position or at a particular height. To be more precise, more scientific, we can say that if I take a mass and keep it at a particular height, let's say mass m or mass m1 is kept at a particular height, let's say of h, then this particular mass will have a kinetic energy possessed by virtue of its position. Whenever I keep any object at a particular position, innately that object will develop an energy within that particular system. And when the object falls now, when the object is released from that particular grip, it has to travel h distance and it is going to impact the ground. meaning it is going to change its velocity. It is going to accelerate this particular distance. So what happens there is that, so the initial stored potential energy is now being converted into its kinetic energy. So it is not that kinetic energy is magically fed into the system. When the coconut was really high up, it was having potential energy, specifically gravitational potential energy. So that particular potential energy is now being converted into kinetic energy as the velocity of the system increases. So as the velocity of a system decreases, it gains more and more potential energy. It is due to its position. Okay, and there is another possibility, that is because of configuration. Configuration just means that the setup of that particular object. For example, if I take a bow and arrow, I'm taking a bow and arrow. So we all know that the great warriors of the old used bows and arrows. So you might have heard about warriors who could stretch the bow till the ears and let go of the arrow that could pierce the opponent's heart and still go to the earth. So how do they do it? Is it that initially this has no energy, right? So when you place an arrow, where does the arrow gain that particular energy or that particular drive to go at such velocity, such staggering acceleration and show such precision? How does that arrow achieve that? Even how does the arrow travel that far, right? So where does the arrow gain the energy from? The answer is again very simple. When you place the arrow onto the bow and you stretch the bow, what happens? The arrow is now in a stressed state. The tension on the string is very evident, right? When we stretch it, it is now changing its particular configuration, that is its setup. So this particular setup or configuration is now different. When it is resting on the string, when it is not stressed, it is not having any energy. That is, if I keep it like this and let go of the arrow would just fall down. But if I stretch it and then let it go, the arrow would go a really far distance. Now, that is because when the string is stretched due to its change in position or rating, due to change in its configuration, that is initial state where it was not stretched. We are only talking about the string now. So initially there was no tension in this particular string, or it was not stressed. Now when I pull it back, what happens? The string is now changing its configuration. It is changing its setup. Now, while I am doing that, that is while I am exerting a force in pulling the string backwards, all the force I have exerted is now converted into work. So you do know what is the definition of work. Whenever I apply a force and displacement is produced, I am doing a work. So when I am stretching the string, I am doing a work. This particular work is now being stored as potential energy of this particular system. To stay in that stressed state, the elastic rubber band or the elastic string is now storing all the work that I have given to that particular system, and it is converted into potential energy and it is being stored in this particular string. When I let go of this particular string, what happens is that entire potential energy is now given to this arrow in the form of kinetic energy. So the energy conversion happens, and that is how the arrow will shoot forward. You can also see this in the case of a rubber band. That is, when the rubber band is stretched and suddenly released, it will release that particular energy. So again, so we can say that potential energy is the energy possessed by an object due to its position or configuration. So that is the definition or the general definition of potential energy. Now based on this, we can see many examples. That is, the examples of potential energy can be either due to its position. That is, it is known as gravitational potential energy. Gravitational potential energy. That is, when we keep a certain mass at a certain position or at a certain height, gravity will be pulling down on that particular object. Now it is resisting that pull and staying in that particular position. So it will obviously have gravitational potential energy due to its position. Okay. Now the next thing is elastic potential energy. That is, in the case of a spring or a stretched out rubber band or a stretched out bow. So that is known as elastic potential energy. And finally, you can also include many other examples, but in second PU, you will be learning about electrostatic potential energy. So you will be learning about electrostatic potential energy. That is the potential energy possessed by static charged particle. For example, when you take a system of charges or a single charge, if you want to bring a charge from infinity to a point also, you have to do work. Now this work is being stored as electrostatic potential energy, and dipole will also have potential energy. All that you will learn in your second PU. So here we are going to learn about elastic potential energy and gravitational potential energy. Mainly the potential energy possessed by an object due to its configuration and due to its position. So initially we are going to learn about gravitational potential energy. So what exactly is gravitational potential energy? Again, I told you, if any object is kept, let's say mass m is kept at a height of h, then automatically gravity will be pulling down on this particular mass. Gravity will be pulling down on this particular mass which is kept at a particular height. Now, instead of sinking down into the ground, the object is resisting that particular pull. Now, this work done is actually being stored as energy in that particular system. So, this particular energy that is stored in the system when it is kept at a particular height is known as gravitational potential energy. And the potential energy generally is represented with the capital letter U. Okay, so here also for gravitational potential energy, we will just use U to indicate that it is potential energy. So again, the equation in order to define gravitational potential energy is that a mass m kept at a height h will experience gravitational acceleration. So in together we can say that gravitational potential energy will be equal to mass times the acceleration due to gravity times the height at which it is kept. All these three will contribute towards gravitational potential energy. So this particular equation is important for you, and it is not a new thing. You have been learning about kinetic energy and potential energy in all of your classes from let's say 5th or 6th or something. So it is not a new topic for you. But remember, so this particular system where a mass kept at a particular position will have an energy possessed by that particular mass, and that particular energy possessed is known as gravitational potential energy. We have seen what potential energy is, we have seen what kinetic energy is. Now we are going to deal with a new type of energy, that is mechanical energy. So what is mechanical energy? Sir, it is the energy possessed by machines. No, it is not the energy possessed by machines or mechanical parts. It is rather, the definition for mechanical energy is that it is the sum of both kinetic energy and potential energy in a system. That is, the sum of kinetic and potential energies in a system together is known as mechanical energy. So, if I take a system, let's take the example of a pendulum, then I can say that if this is a pendulum, then I can say that due to its configuration right now, mass m, a bob of mass m hung from a string, let's say of height h, will possess what? Gravitational potential energy, because it is just simply hanging. A mass is just simply hanging. Gravity will always be pulling down on it. Hence, it will have gravitational potential energy. But when it is swinging, automatically it will have kinetic energy. So I'm assuming a case where I have kept this particular pendulum here. Okay, I've raised this pendulum. Okay, I have raised the bob and I've kept it here ready to let go. So the moment I let go, it will start to swing. Just the second before that I let go, this particular mass is now at a particular height. from the mean position. I'll take this as the standard position for measuring left or right. So if I say that, okay, from the mean position, I'm keeping it up at this particular height, then obviously it will have potential energy due to its configuration or due to its position. Then I can say that as soon as I let go, this potential energy of the system is now being converted into kinetic energy. So gradually, as it moves, as it gains velocity, what happens? As it gains velocity, kinetic energy of the system increases gradually while potential energy of the system decreases gradually. So you see, it is not a new energy that is being given to this particular system. Initially, it was at a position, it will have maximum potential energy. But as soon as I let go, this ball is going to drop. So as it is dropping down, it will convert its potential energy slowly into kinetic energy. So now kinetic energy is being increased. Kinetic energy is maximum at the mean position and it will start to swing to the other side. But as it goes to the other side, the kinetic energy gradually decreases. Now, again, when it reaches this particular position, when it reaches the opposite side, what happens? The kinetic energy will be completely used up. Now again, it will be slowly, this particular using up of kinetic energy is now being converted into potential energy. That is, kinetic energy is maximum here. Now it is going to reduce and become zero, which means potential energy will start to increase, become maximum. So this process will happen again and again and again until the bob gradually slows down due to air resistance. So a system is now converting kinetic energy and potential energy with each other. So initially potential energy, gradually it becomes kinetic energy, and then again potential, kinetic, like that. So if I want to say what is the net energy of this particular system, just kinetic and potential, then I'll say that the mechanical energy of this system is, so that particular energy, that is the sum of kinetic and potential energy together, are known as mechanical energy. Okay, so mechanical energy, the definition of mechanical energy is simple. It is, mechanical energy is defined as the sum of kinetic and potential energies of a system. Now, there is one important condition for this mechanical energy is equal to kinetic plus potential to occur. Now, there is one important thing you have to understand, that all energies are conserved in flat space. Or for you, energy is conserved. So, if I say or if I try to explain conservation of mechanical energy, then there is one important condition. That is, mechanical energy can only be conservative, or mechanical energy can only be conserved if the work done on it is by conservative forces. Now, what is conservative forces? Are there any non-conservative forces? Yes, there are conservative forces and non-conservative forces. I'll give you a brief description about what is conservative and non-conservative forces very soon. But for now, just understand that there is conservative forces, forces which are conserved. Essentially, the work done in a closed cyclic process will be equal to zero for them. That is, all these mathematical definitions are there for conservative forces. Conservation of forces or conservation of any quantities just means that it will follow a certain symmetry. That is all a bit technical. I'll explain what is conservative and non-conservative forces very simply to you. But for now, understand that if mechanical energy is to be conserved, then the force applied on the system should be by conservative forces. There is a type of forces known as conservative forces. Some forces are not conservative. For example, viscous force, frictional force, all these forces are not conservative forces. But there are forces which are conservative in nature. For example, strong force, electrostatic force, and magnetic force, all these forces are actually conservative. But there are a group of forces which are not conservative. So, for mechanical energy to be conserved, work done should be done by, or the force applied on the system should be by conservative forces. So, for conservation of mechanical energy, that is conservation Conservation of mechanical energy is only possible when mechanical energy of a system remains constant only if forces doing work on it are conservative. So if the forces are not conservative, then the mechanical energy of that particular system is not conserved. So conservation of energy is true, but there are certain conditions to be applied on it. And for you, as far as you're concerned, here the particular condition is that if the forces doing work on a system is not conservative, then the entire mechanical energy of that system is not conserved. And mechanical energy of a system is nothing but kinetic plus potential energy. So yeah, I told you that if conservative forces are doing work on an object, then work on a system, then the mechanical energy is conserved. So we do know that, or you should know that, gravitational potential energy, or simply gravity, is a conservative force. We can say that the gravitational force which is pulling down on any object is actually conservative. So if that is a conservative force, then by the definition we just learned, mechanical energy of a system should be conserved if gravity is acting on it. So I am taking an example where an object is under free fall. That is, let's say mass m is freely falling down, and I have taken 3 random positions. That is, initially when it is kept at a particular height. Let's take a coconut. So a coconut is at a particular height, and suddenly the coconut starts to fall. And when it is midway through its journey, I took this particular position, let's say at a random position, let's say after x distance or something. So that is position number 2, and we have position number 3, which is when it is just about to strike the ground. So all these 3 positions are taken because I am going to find out what is the mechanical energy of this particular system when it starts to fall, when it is midway through its fall, and when it is going to impact the ground. So according to conservation of mechanical energy, the sum of kinetic and potential energy should be same. That is, mechanical energy of this system should be same here, here, and here. In position 1, 2, and 3, the mechanical energy I obtain should be same throughout. If it is not same, then obviously conservation of mechanical energy is wrong, because gravity is a proven conservative force. So let's find out what is the mechanical energy of this particular system. So assuming that mass m is the one falling, we don't know what is the velocity of these objects in positions 1, 2, and 3. So we obviously have to derive a relation between velocity of that particular object in terms of the quantities we do know. So the quantities we do know is that the object is falling from a certain height of h, okay, and we are going to measure the speed of the object or the mechanical energy of the object at position 2 after x distance. Obviously, the remaining distance will be h minus x. And the last thing we do know is that it is gravity that is pulling down on this particular object. That is, during free fall, gravity is the one who is accelerating the particular object, which means g is always acting downwards, and it is gravitational or simply acceleration due to gravity that is pulling down on the object. One general doubt is that, okay sir, now g is there, should I take it as negative? You don't need to take it as negative, because we are measuring the motion downwards and the direction of g is also in the downwards direction. So we don't have to take g as negative. So, but the problem is that, okay, for gravitational potential energy, we do know that it is mgh. There is no problem. So potential energy of a system will be mgh, no problem. But mechanical energy of a system is Ke plus Pe, kinetic energy plus potential energy. But we don't know what is the potential energy of this particular system. But we don't know that what is the kinetic energy of this particular system when it is falling. At each instance, we don't know what is the velocity of the object. Okay, initially we do know that v is equal to 0. At this particular position, v will be equal to 0. Let's call it as v1. v1 will be equal to 0. But what will be v2? Or what will be v3 when velocity is at maximum? What will be that value? So we don't know what is velocity in all these 3 cases. So we can take it as v1, v2, v3, but we don't know the values of v2 and v3. v1 is equal to 0 because it is just about to fall, meaning the velocity at position 1 will be 0. So how can we derive a relation between V and the known quantities that is existing here? That is why we have equations of motion. So that is why we studied equations of motion, so that we can have tangible relations in cases like this. So I'm taking the equation, let's take V square is equal to U square plus 2AS. U is the initial velocity, A is the acceleration, S is the displacement produced. We are going to use this particular equation and we are going to find out what is the velocities or expression for V in all these three cases. So we don't have to take what is the velocity for the first case because it is just about to fall, that is, it is just going to be in free fall. So we don't have to take the velocity of the first position because automatically it is written down as 0. So V1 will actually be 0. Now we are going to start with position number 2, that is, the object is in rest, it is now just starting to fall, and when it reaches position number 2, let's say after x distance, what will be the velocity of that particular object? So in order to find out what is the velocity at position 2, we use the same equation. We'll say that V1 is equal to U square. U square is nothing but the initial velocity. Initial velocity is nothing but 0. So 0 plus 2 into G because every motion is happening downwards. Our reference direction is downwards. Gravity is also in the same direction. That is why we are not taking G as negative. So we can say that it is equal to 2G into what is the displacement? The displacement we are measuring from this particular distance. So now it has only traveled x distance, not h distance, but rather x distance. So we can say that it will be 2gx, or V1, velocity 1 will be given by the equation 2gx. So this, let's call it as equation number 1. So this will be the first equation we get, that is V1 is equal to 2gx. Now what about position number 3? At position number 3, what will happen? So again, this is V2, not V1. V1 is already equal to 0, right? We are measuring the velocity at position number 2. So we can say that V2 is equal to, or V2 square is actually equal to U square plus 2AS, or simply V2 square is equal to initial velocity 0, 0 plus 2gx. That is equation number 1. Similarly, at position number 3, we say V3 square is equal to, that is velocity at position number 3, velocity at position number 2, velocity at position number 1. So V3 square is actually equal to, again, V1 square, that is 0 plus V1 square plus 2AS. 2 into A is nothing but G, and what is S? S is nothing but H, because now it is reaching the ground position. So the entire distance is now covered. So from 0 to H it has covered. So the displacement will be H. So V3 will be given by, or V3 square will be equal to 2GH. Now that is our second equation. Now we have three equations. One is V1 is equal to 0. Second one is V2 is equal to 2gx. And the third one is V3 is equal to, or V3 square is equal to 2gh. V1 square, V2 square and V3 square is now being given. Now we are going to find out what is the mechanical energy of the system in position 1, 2 and 3. So mechanical energy ME is equal to KE plus PE. So automatically at position number 1, mechanical energy is equal to, kinetic energy will be 0 because there is no velocity. V1 is equal to 0. So 0 plus potential energy of that particular system. When a mass is kept at a particular height, it will be mgh, right? So it will be equal to mgh. So the mechanical energy of position 1 will be equal to mgh. So if if conservation of mechanical energy is true, then mechanical energy of the system will be same in position 1, 2 and 3. So that is what we are going to prove or going to try to figure out. Let's see if it will be true or not. So at position 1, we can say that mechanical energy is equal to mgh. Now what about position number 2? When the object is falling and it has, let's say, traveled a distance of x through, then we can say that mechanical energy of the system at position number 2 will be equal to, kinetic energy is now existing, there is a V2. So we can say that, and V2 was equal to 2gx. So we do know what is Ke plus Pe. It is half m V2 square plus mgh. That is the general definition, which is equal to half into m into V2 square is equal to 2gx plus what is the potential energy of that particular system. Again, we know that mass is falling through an height, right? It is falling through a height of h after a distance of x. In position number 2, we are going to measure what is the kinetic energy of the system plus potential energy of that particular system. Now, since it has traveled through a distance of x, we can say that it is now at a position, this particular height is nothing but h minus x. Okay, now the potential energy of a system will be, the mass is now sitting at h minus x distance. It is not at x distance, it is h minus x, because potential energy is being measured from the ground up, gravitational potential energy. How high is the object? Now the object, while it is falling and reaching position number 2, then the object is at a position of h minus x. So it will be at mg, instead of h, it will be h minus x. Now, if we simplify this particular equation, we will get half and 2 will cancel out, and it will be mgx plus mgh minus mgx. So minus mgx and plus mgx will cancel each other out, and we will get mgh. So at position 1 and position 2, we got mgh. Now finally at position number 3, same trick. That is, when it reaches position number 3, what will be the net mechanical energy? So mechanical energy at position number 3 will be equal to, again, half mv square plus mgh. So half mv square plus mgh, which will be equal to half m. Instead of v square, we have an equation to find out what is the velocity at position number 3 when it has covered the entire distance, that is h. So obviously here, instead of x, we will have h. That is, it has completely covered all the distance. So half into 2gh plus, what will be potential energy of the system? What will be the potential energy? It will be 0, because it has now covered the entire distance. Entire potential energy is now being converted into kinetic energy. There is no height to be measured from the ground. If there is no height to be measured, then obviously potential energy U is equal to m into g into 0, which is nothing but 0. So we can say potential energy of the system will be equal to 0. Half and 2 will cancel each other out, and then we can say that it will be equal to mgh. So we have actually proved that in position number 1, in position number 2 and in position number 3, the values of mechanical energy is equal to mgh, which means mechanical energy is a constant when the force doing work on it is conservative. Hence, mechanical energy conservation is proved. So if they ask you to prove or illustrate conservation of mechanical energy, you can consider a freely falling object with initial velocity 0 and use this particular derivation to show them that, okay, mechanical energy is conserved. I hope you have understood all about whatever I have said here today. I'll meet you all in the next class with an interesting topic. Until then, thank you.